Okay, so this is section 8.3, and in this case, it's going to be really similar to 8.2, except this time our samples are going to be dependent. So what does that mean? That means that we are going to have paired data. So the sample data points from one set correspond to points in the second set, okay? So in order to perform the test, we're going to have to find our difference. And in this case, our difference is going to be the first data value minus the second data value. We find the mean by adding up all those differences and dividing it by the total number in the paired data samples. Okay, so we have a few things that we need to keep in mind, and they are our samples have to be randomly selected. And so since I accidentally hit, oh, no, I thought it was on the highlighter. I was excited. Ah, there we go. So our samples are paired. Our population has to be normally distributed, or our sample size is at least 30. Okay. And then if the conditions are not met, we can approximate D-bar. Okay, so we're still going to be able to do it. It just, we probably are going to have some errors. Okay, and then just like we were working with before, n-1 is your degrees of freedom. Okay. All right, so let me run through the steps. So remember, n stands for the number of pairs. Okay, our difference is going to be, why is it not highlighting? Okay, let me see, switch. Okay, that's fine. All right, our difference is x1 minus x2, and the hypothesized mean is the difference between the paired data. Okay, so with this test, we are going to be checking to see if our differences are not equal, or sometimes they could be less than or greater than. Okay, so there is a difference, and we'll go through a few examples where I showcase that. So our formula to find the mean of the differences is shown here. And then the standard deviation of the paired data, we're going to be pretty much using this formula just because it's going to be easier for us to work with based on our data. Okay, and essentially it's the same thing. They just used our summation rules to simplify the numerator. Okay, so our test statistic is represented by D-bar. And once we have that information, we can find our standardized test statistic represented by the following formula here. And remember, your degrees of freedom is going to be n-1. Okay, so just like we've been practicing, you're going to verify that your samples are random and dependent, or and also normally distributed, or at least n is greater than or equal to 30. You're going to state your claim and then identify your null and your alternative hypothesis. Identify your level of significance, and it's always good to, when you're identifying your null and your alternative hypothesis, to determine if the test is right, pen is being finicky, right, left, Okay, come on. Okay, I'm gonna use this for right now. Or 2-10. And then I'm gonna restart once I finish this part before I do the examples. Okay, so degrees of freedom is n-1. Table 5 in your book, it's on page A18. Has your critical values, and then we've got our formulas here. So you're going to find your standardized test statistic, and then from there, if the t-value from your standardized test statistic formula is in your rejection region, obviously you reject H0, otherwise you fail to reject. And then, as always, we're going to write our final sentence. Okay. All right, so okay, so our first example here. We have a shoe manufacturer is claiming that athletes can increase their vertical jump height using the manufacturer's new training shoes. The vertical jump heights of 8, so that's my N. Randomly selected athletes are measured. The athletes have used the training shoe for 8 months. Their vertical jump heights are measured again. The vertical jump heights, blah, 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 are shown in the table. Assuming the vertical jump heights are normally distributed, is there enough evidence to support the manufacturer's claim at an alpha level of 10%? Okay. So the first thing that I'm going to do is I'm going to write down my claim, and I'm going to need some more room. So okay, so leave yourself a little bit of space because we're going to need to add to the table here. But our claim is that the new jump height is supposed to be greater than our old jump height, right? So when we're doing our difference, if the new one is going to be greater when I'm subtracting the old height minus new height, I should be getting a number less than 0. So my claim is the difference in my mean is going to be less than 0. Okay, so the complementary statement to that is going to be the difference in my mean is going to be greater than or equal to 0. Okay, so we have the alternative hypothesis here, and my null is here. Okay. Okay, so the next thing that I'm going to do is I am going to calculate my difference D. Oops. So a difference is going to be x1 minus x2. So in this case, this is x1 and this is x2. Okay, so I'm going to go ahead and calculate the difference. So I'm going to do 24 minus 26. So I'm going to get -2, -3, 0, -1, 2, -2, -5, and -3. And I'm going to need the sum of that. So I'm going to go ahead and calculate the sum by adding them all together. And I'm going to get -14. Okay. All right, so the other thing that I'm going to do, and I kind of ran out of room a little bit, is I'm going to square each of these because I'm going to need that. I'm going to need that later for one of the formulas. Okay, so D squared. So we'll get 4, 9, 0, 1, 4, 4, 25, and 9. And I'm going to add that as well to give me 56. Okay. So now what I'm going to do is I am going to calculate D bar. Okay, so D bar is the sum of D divided by N, which in this case is -14 divided by 8. So I'm going to get negative 1.75. Okay. All right. The next thing I'm going to do is I'm going to calculate my standard deviation. So I'm going to use that second formula that was on the list. So the square root of the sum of d squared minus the sum of d squared divided by n, all divided by n minus 1. All right, so that's going to give me the square root 56 minus the sum of d was negative 14 squared divided by 8 all over 8 minus 1. All right, so if I plug that in, I'm going to get about 2.1213. Okay, so now that I have all of that, I am going to find my test statistic. But actually, before I do that, let me find my critical value because I haven't done that yet. And I should have done it. All right, so in this case, we've got a left-tailed test. Okay, so what I'm going to do is I am going to use my calculator to find my t-value. So I'm going to do second bars, and then I'm going to use my inverse t. And my area, in this case, since it's left, I don't have to do anything. It's just going to be 0.1 from my alpha level. So remember, if it is right-tailed, you have to subtract 1 minus this. And if it is two-tailed, you're going to divide this by 2 because we have 2 rejection regions. And then my other thing that I need is my degrees of freedom, which in this case is 7. And if I do that, I'm going to get a critical value of negative 1.415, which tells me, since this is a left-tailed test, anything less than negative 1.415 is in my rejection region, okay? All right, so now let's find that critical value. No, I lied. We found the critical value. Now let's find our standardized test statistic. Obviously, it's early and the coffee has not kicked in yet for Megatech. Okay, so my formula is d bar minus the difference in our means. Madison might be awake. Gotta hurry up. All right, divided by my standard deviation minus divided by square root n. Okay, so d bar, we got negative 1.75. The difference in the mean, we're trying to see if it's less than or greater than 0. So we're going to assume that the difference is 0. My standard deviation, we got 2.1213 divided by the square root of 8. Okay, so if I do all that, I'm going to get negative 2.33. So the question is that in our rejection region? And the answer is yes. So we're going to reject our null. Okay, so from there, let's write our sentence. There is enough evidence that a 10% significance level to support the claim that the athletes can increase vertical jump using key training shapes. That was probably a little wordy. Okay, so we're going to repeat example 1, except we're going to do this in the calculator now. So our calculator steps are as follows. What you're going to do is you're going to first enter in the lists. So you're going to go to stat and then edit and then enter your list. So in this case, in list 1, it's going to be the before values, and in list 2, it's going to be the after. And then what you're going to do is you're going to put the difference in list 3, but you're not actually going to type all the numbers in, okay? So what you're going to do is you're going to go, when you're on list 3, you're going to go up into the top bar part where list 3 is highlighted. And then what you're going to do is you're going to say list 1 subtract list 2. So to do that, you're going to use the alpha and then the 1 key, because that is list 1, and then alpha and the 2 key to get list 2. Okay, so let me see, how can I type that? Put L1 minus L2 in the top bar. Okay, so this way it'll calculate the differences for you. You don't have to type them all in and find it, because then that's kind of like defeating the purpose of doing your calculator. Okay, and then from there, you're going to go to stat. And then test. And then when you're in your test mode, you're going to click on t-test. T-test. And then, okay, so you'll notice it has 2 options for your input, data or statistics. We've been working with statistics, but in this case, we're going to use data now because we just typed into the list. So some things to keep in mind, it's probably under Greek. Yeah. Okay, so mu naught is going to be 0. Your list, you're going to put L2, L3. Your frequency, you're going to leave that as 1. And then it gives you the 3 options for your different testing. So in this case, you look at the alternative, which is less than mu naught, and then you're going to go down to calculate. Okay. So, and then once you do that, you'll notice that we're getting our p-value and also our t-value. Okay, so you can use the t-value for rejection regions, and you can use the p-value to see if it is less than or greater than your alpha to determine if you reject or not. Okay. All right. Let's do another example. Okay, so in this case, we have a state legislator that is trying to determine whether or not her performance rating has changed from last year to this year. This chart is on page 454 for you, but I went ahead and copied it. So we have 16 randomly selected voters, and our significance level in this case is 0.01. And let's see if this has changed or not. Okay, so what we're going to do is we first are going to list our claim. Give myself more room because I know I'm gonna need it. Okay, so the claim is that there is not a difference. Oh, the claim is that there is a difference. Oh my gosh. Okay. Take two. The claim is that there is a difference, and so therefore the difference is not equal to 0. And my null in this case is going to be that the difference is equal to 0, therefore there is no difference in her ratings. Okay. Okay, so this one is H naught and this one is HA. Okay, now we're on track. All right, so I'm going to be doing a two-tailed test in this case. So that means when I find my t-value, I can do this in the calculator. I can do inverse t. And I have to divide my alpha level by 2 since I have 2 rejection regions. And my degrees of freedom in this case is going to be 15 because I have 16 total for my n. So if I do that, I'm going to get plus or minus 2.947, which means it looks like this, where I have a rejection region of less than 2.947 and greater than 2.947. Okay. So now that I have all of that, let's go ahead and calculate the rest of the things that I need. So we're going to calculate our d bar. Okay, so to do that, we're going to take the sum of d and divide it by n. So in this case, it's 53 divided by 16, which is 3.3125. All right, and then we'll find our standard deviation. Okay, so that is the sum of d squared minus sum of d squared over n minus 1. All right, so let's go ahead and plug in. We are going to get 1581 minus 53 squared over 16 divided by 16 minus 1. All right, so if I plug all that in, I'm going to get, what, 9.68? Okay. All right, so now we can find our t-test statistic. So we're going to get d bar minus mu d all over standard deviation. Okay, so 3.3125 minus 0. Really don't mess with my papers. 9.68 divided by square root of 16. All right, so we're getting a t-value of 1.369. Okay, so where is that on my chart? It is here. So is that in the rejection region? And the answer is no. So we're going to fail to reject. Okay, so let's go ahead and write our summarizing sentence. at the 1% significance level, there is not enough evidence to conclude that the legislators' ratings have changed. Okay, last thing that we're going to do is we're going to determine our confidence interval for our data set. So just like you guys did before, we are going to enter data A into list 1, data B into list 2, and put the difference in list 3. So remember, when you're doing that, you're going to scroll all the way up to the top and put the setting that the list 3 data is list 1 subtract list 2. Okay, so list 3 is going to be list 1 list 2. And remember, you type that in the top portion. Okay. All right, so after you're there, what you're going to do is you're going to click stat and then test and then t interval. Okay, so then from there, pull my calculator. Okay, so stat, test, t interval. So you're going to click data again, and your list is going to be list 3. Frequency, leave that as 1, and your confidence interval level is 0.99. Okay, so then after you have that, you're going to click calculate, and then it's going to give us -3.692 and 2.617. Okay, so what that is telling me is with 99% confidence, the difference in the means for my data is going to be between -3.692 and 2.6117.